In this video, I'm going to talk about two important tests, the integral test and the P-series test, for determining convergence or divergence of infinite series. So our integral test is if the function is positive, continuous, and decreasing. So you have to state those conditions for all x greater than 1, and you can basically use improper integrals to determine convergence or divergence. So if the improper integral converges, your series is going to converge. If your improper integral diverges, then your series is going to diverge. Now keep in mind that the sum of the series is not necessarily the area under the curve. So even though I might be able to find a value, it's not going to tell me what the actual value is. Okay, use the integral test to determine convergence or divergence. So we want to look at this first example. And writing this, if I plug in 1, we get 1/2. If I plug in 2, 4, 5. If I plug in 3, we get that. So our function, remember we need to state the conditions. Okay, so now I can say that the limit as t goes to infinity from 1 to t okay, so I'm looking at the limit as t goes to infinity. The antiderivative of this is inverse tangent from t to 1. So I have the limit as t goes to infinity of inverse tangent of t minus inverse tangent of 1. As I go to infinity, this value goes to pi over 2. This value is pi over 4. So this converges by our integral test. Okay, next one. I have, when I plug in 2, I get 2 ln of 2 plus 3 ln 3 plus 1/4 ln 4. So this is a positive, continuous, and decreasing function. So I take the limit as t goes to infinity of 2 to infinity of 1 over x ln x dx. That's a u substitution, just so you guys realize that. So it would be, the antiderivative of that is ln of the ln of x, because your u is ln x, your du is 1 over x. Evaluated from 2 to t. So I have the limit as t goes to infinity of the ln of the ln of t minus the ln of the ln of 2. Well, as I go to infinity, this value, ln of infinity is infinity, so I'd have basically an infinity minus whatever this value is. So this diverges by our integral test. Okay, P-series. And we talked about this when we did improper integrals. And that's why I talked about that test during that section. So, P-series in simple and harmonic series. So if P is a positive constant, just reminding you what a P-series is, okay, where you have your value and P is now in your exponent. And if P is less than 1, so if your value is less than 1, that series is going to converge, but if you're between 0 and 1, the P-series diverges. And a common one is a harmonic series, where P equals 1, and that is actually going to diverge because P is between 0 and 1. Okay, so looking at this one, let us look at what that exponent is. On the bottom, really that exponent is n to the 3 halves. Since P is greater than 1, since P equals 3 halves, and 3 halves is greater than 1, by our P-series test, the series converges. But I'm looking at this now. I'm looking at this. If P is less than 1, I'm guessing, going back, this should say P is greater than 1. That's why on that last slide I was a little confused. If P is greater than 1, you're going to converge. But if P is between 0 and 1, then you're going to diverge. Because if you think about this, this doesn't make sense, because it's the same thing. Okay, sorry. Quick edit on that. Okay. Looking at the next one. That's why I was so confused. I was very confused on the last one. When I was looking at that example and I'm recording it, I'm like, wait, I feel like they're saying the same thing. Anyway, okay. So we get 1 over n to the 2/3 there. P, which equals 2/3, is less than 1. So by the P-series test, the series diverges. Okay. What did I want to say on this one? I can't remember. Oh, that's what I wanted to say. Make sure, again, that you're stating the test. You need to state the test that you are using. Okay, and then the conclusion that you have. Okay, that is it for today on this one.